Okay, so in the first part of this lecture, we covered the foundations of a Newtonian theory, talks about spherical and nearly spherical bodies, and provide this sort of general Newtonian equation for arbitrarily shaped bodies that are small compared to their mutual separations. Then, of course, we specialized to the simple sort of textbook two-body problem, which most of you have seen before, at least at some level. But now we want to turn to a more realistic set of problems where the second body, the two-body system might be perturbed in some way. So what might those perturbations be? Well, since our original Keplerian two-body problem was of 2-point masses or two spherical bodies, one of the bodies might be non-spherical, might have multiple moments. How does that change the orbit? There might be a third body in the system, a binary system being perturbed by a third body, or one of the planets in the solar system being perturbed by the gravitational force of the third body. Or a black hole orbiting a supermassive black hole inside a nuclear cluster of a galaxy being perturbed by the whole swarm of other bodies in that system. How might that work? And of course, you could have a two-body system in isolation, but where you now turn on general relativity, which changes the law of gravity from the Newtonian one and is going to induce perturbations. So the real world has lots of perturbations, and to the extent that they are small, we'll now discuss a way that which you can solve for orbits in a perturbative sense by including these extra bits. So the first thing we have to do to try to approach that is to talk about the two-body orbit more generally. Before, in the simple two-body problem, we always put the orbit on the xy plane because of spherical symmetry. The orientation of the orbit played no role, but now it might, because you might have your system orbiting like this, but being perturbed by a third body that's in an orbit that's not in the same plane. So clearly the orientation of this orbit relative to the third body matters. You might have an orbit, two bodies in isolation, a black hole orbiting a spinning Kerr black hole, but the axis of that Kerr black hole might be pointing in a different direction than the normal to the plane of your orbit. So the orientation of your orbit relative to the black hole matters. So we have to first talk about orbits from a general point of view and define how to describe a completely general orbit in this context. So the first thing I want to do is talk about Keplerian orbits, but Keplerian orbits in space, in some arbitrary orientation in space. So here's the idea. We first define a reference plane for our system. It's simply a coordinate system that we're going to use to describe this orbit. The xy plane is the reference plane, and the z-axis is the perpendicular plane. In the solar system, this is called the plane of the ecliptic. It's kind of an average orbital plane that defines the plane of the solar system. Most of the planets have slight tilts relative to that plane, but that plane is the reference plane for the solar system. For a binary pulsar, the reference plane is the plane of the sky. So it's perpendicular to our line of sight, and it's the plane of the sky, and the orbit might have some inclination relative to the plane of the sky. In fact, for most astronomical observations, the plane of the sky defines the reference plane. If you're worrying about an orbit around a supermassive black hole, you might define the equatorial plane of the supermassive black hole as the reference plane with the spin axis perpendicular, and then your orbit might be in some random orientation. Okay, so given a reference plane, we want to define our two-body Keplerian orbit. We'll get to the perturbed case in a moment. So we know that so first we define the orbital plane. And we know for a pure Keplerian orbit that orbital plane is fixed, whatever it is, and we define the inclination of that orbital plane relative to the reference plane. So it's this angle between the plane of the orbit and the reference plane. Another way of stating it is that the angular momentum of our Keplerian orbit, which is perpendicular to the orbital plane by definition, if you take the dot product between that and this z-axis, that's just the cosine of the inclination. It's the cosine of this angle. There's z, and there's h pointing in this direction, so cosine of I, and that's I. So that defines the inclination of the orbit. Now, if this orbit is inclined relative to the reference plane, there'll be a line of intersection between those two planes. And you define an angle from the x-axis, this is just the convention, from the x-axis to the line where the orbit goes from below your reference plane to above your reference plane. That assumes a particular direction c, as the line of the ascending node. Again, one of these celestial mechanics terms that I have no idea where it comes from, but that's it. It's ascending, it's coming up from below the plane to above the plane, and it's node, whatever that is. Okay? But anyway, this is the line angle of nodes, and the angle of the ascending node. Another way of defining that mathematically is that if you take h and dot that into EY, this reference plane, that's going to be proportional to sine I, but it will give you this angle. So the cosine of this angle is given by h, the angular momentum, dotted into the y reference direction, divided by sine I. And the limit that I goes to 0, of course, that thing blows up, but it just means that this nodal line is not defined when the two planes are exactly the same. Right? You can't define where they intersect if they're the same plane. So things go a little singular when I is 0, but that's a common problem. But for any inclined orbit, then this is the pictorial definition of the angle of nodes, but here's the mathematical definition in terms of h and the other EY. Okay, so h, this constant of motion, again, we're still on the Keplerian problem. H defines the orientation of the orbit in space. Then we have the angle of pericenter. Within the orbital plane, we have, and let's just for now talk about elliptical orbits. Obviously, we can talk about hyperbolic and parabolic, but let's talk about elliptical orbits. So within this orbital plane, the separation vector has a pericenter somewhere, let's say here, closest approach. So there's an angle that's defined starting at the ascending node to the angle at which the pericenter occurs. And again, so that's a pictorial definition of the angle of the pericenter, but you can define it mathematically, and you can show that it's the run lens vector dotted into EZ, so it's sort of this angle here, but then you have to divide by E sine I, because that's the overall factor. In the circular orbit limit, there is no pericenter, so you don't define the pericenter. And for zero inclination, there's a sine I factor here, and so for zero inclination, the angle of pericenter and the angle of the ascending node become degenerate, and so it's really the sum of the two angles that counts. So if this plane is on that plane, then from the x-axis you go all the way to the pericenter, because this line kind of disappears. So again, coplanar orbits they get a bit. You have to worry about some singular issues in this representation, but as long as the planes are different, then that's the definition of the angle of pericenter, the mathematical definition. Okay. How elliptical is it? That's defined by this eccentricity that we talked about, and we know from the previous thing that's just the magnitude of this run lens vector. And the final constant of motion, the semi-major axis, is just related to this P, the semi-lattice rectum, another name from celestial mechanics. And it's just defined by h squared divided by gm and 1 minus e squared. So that defines roughly the scale of the room. And there's a final constant of the motion that we won't really discuss very much, because it's really only important if you're really doing actual timing of orbits, and that's the time of pericenter passage. It's the time, in terms of whatever time you're doing, at which the orbit passes the pericenter. And that's defined in a particular way as an integral of the true anomaly from 0 to the true anomaly where you are at that particular moment of time. So these 6 variables, these 6 constants, I, omega, little omega, E, A, and T, are completely equivalent to the 6 initial conditions of the orbit. We have a second order differential equation in time, right? So you have to have 6 initial conditions to describe the orbit. 3 components of x, 3 components of v. Once you have those, you have the complete solution for all time of the orbit. And those 6 constants, the 6 initial values, are completely equivalent to these 6 constants. The time of a certain periodic passage, this. So, in fact, there's a way to transform from one to the other. You can even be fancier in using things like canonical transformations from Hamiltonian and Jacobi theory. You can make very formal and fancy ways of discussing how to relate the 6 initial conditions to the 6 constants of the motion. Okay, so this then describes a general orbit, general pure Keplerian orbit in terms of 6 things. 3 that give the orientation, 2 that give the scale and shape of the orbit, and 1 that kind of tells you where time started. It initializes the orbit in time. Generally speaking, we're not about time itself, but what happens to the shape of the orbit as the orbit evolves and other things. So we rarely deal with this. This is if you're really doing celestial mechanics and you want to know when that spacecraft actually passes a certain point next to the planet that you're aiming for. Time really matters. Okay, any questions about this setup? Okay, now we want to perturb this thing. We want to go from a pure 2-body Keplerian problem, defined by this equation of motion, to one in which there is a disturbing acceleration. The celestial mechanics literature is always called a disturbing force, which is strange because it's really an acceleration. That's what they say in these celestial mechanics books. So I will often say disturbing force, but just remember it's really an acceleration, but it's F, I use F. It's some force, depends on R, the separation of your 2 bodies, depend on their velocities, could have some explicit time dependence, and this will encapsulate all the perturbations of your system. Third body, quadrupole moment on one of the bodies, general relativistic effects, blah, blah, blah. So how do we describe the situation when we have this perturbation? If we have a nice exact solution in Newtonian theory, what do we do when we've got this thing perturbed? Well, the way I want to describe is what's called oscillating orbit elements. Those 6 constants that I talked about before, E, A, omega, little omega, are called orbital elements of the orbit. But here we want to talk about oscillating orbit elements. Now, the way we do that is to take our orbit, some particular x at some moment of time, and some v at that moment. Okay, it describes the orbit at some moment of time, and make the following definitions. The separation x is just r times the unit vector, where r is the size of the separation. These are all definitions. And this r, the distance between the 2 bodies, is defined to be p over 1 plus e cosine f. That's a definition. P will further be, P is just a proxy for this A, the semi-major axis. And the eccentricity of 1 by c squared, that's the formula. Often we go interchangeably between the semi-lattice rectum, the semi-lattice rectum and the semi-major axis. But that's the formula in a definition. The velocity at that point is defined to be this. H times E sine F over P times N, the radial unit vector, plus H over R times lambda, a vector that's perpendicular to the radial unit vector. This is like the R dot, right? If R is R times N, you want to get dr dt, so you get R dot times N. Well, this is just R dot. And then you get R times dn dt. Well, dn dt, the rate of change of a unit vector, has to be perpendicular to the unit vector. Definition. So it's this lambda unit vector, and this is the dr dt times r. Okay, so that defines the velocity. And h is related to p by this definition. Now what about this unit vector that points to in the direction of our orbit? It has some orientation relative to our reference plane. What is that orientation? It's defined by these equations. Unit vector It's given by, here, this shows the angle of nodes, there's the pericenter angle, there's the true anomaly, this is like phi, there's the inclination, lambda is there, and then h is just by definition the cross product of these two, and cos lambda is h, perpendicular to the orbit. Let's get away with this. So this takes our actual orbit, which could look something like this, right? Some weird orbit being perturbed by interacting with some other bodies, and defining it to be that Keplerian orbit that has the same x and v as this orbit at that moment of time. So it's, take this moment of time, this actual orbit has a particular x and v. This is the Keplerian orbit that would have the same x and v as this one at that moment of time. It's called the oscillating orbit. Oscillate is a word from Latin that means to kiss. So you're just touching the orbit, it's tangent to the orbit, so it's just a touch. So it's the oscillating orbit. So this is the pure Keplerian ellipse that coincides with that orbit then. Now this is a weird orbit at some later moment of time, has the same x and v. At some later moment of time, it's the orbit that is oscillating to the orbit here might have different values of the orbital elements than this one. So we make these definitions now, but we don't expect E, omega, big omega, or I to be constant anymore. They could vary because this may not be the same Keplerian orbit as that. Why do they vary? They vary because of those perturbations. Okay? The thing is, if the perturbations are small enough, then the orbit is almost a completely Keplerian orbit with constant values of A, E, omega, etc. And if these are weak, if these perturbations are weak, then the variations in these quantities, which are hitherto constant, might be small. And so you can do perturbation theory with inconstant initial values and then small deviations from those initial values because of the perturbation. And so that's the kind of heart of this oscillating orbit method. We can define, make an exact Keplerian definition of the orbit, but now the constants are no longer constant. This is something you do in mathematical physics all the time. You have some complicated equation that might look like a harmonic oscillator, but maybe there's a forcing term. Well, you define your solution to be a harmonic oscillator with a varying frequency, and then you separate things into slowly varying and rapidly varying bits and so on. It's a variation of constants methods that you should be familiar with from standard mathematical physics. So this is just variation of constants in a specific context. Okay, so that's all that. Well, let's give an example of how this might work out. How could we figure out how these various quantities, constants, change if we have this disturbing force? For example, here is our definition of the angular momentum, is r cross v. That's a definition. Here's our definition of the Runge length swing. What's the rate of change of h? So dh dt, well, v cross v is 0, so we just get r cross dv dt, but the first term gives 0. That's the whole point of the Keplerian problem. But so we get r cross f. Okay? So already we see that dh dt is r cross f. And what's r cross f? That's the torque being exerted on this two-body system. So the angular momentum changes if there's a torque. If f were purely radial, there'd be no torque. So f has to have a component either in the lambda direction or the h direction to make h change. What about dA dt? Well, crank out the formulas and plug in everything that you need to do, and you find that dA dt is f cross h plus v cross r cross f. Yeah, that's simple work out. So if there's an f, you learn how these things change. And remember, these are all related to our orbital elements. So let me give one example of calculating how one orbital element changes with time, and then I'll just list all of the equations for all the orbital elements. The key, of course, is to take this f and decompose it into a radial direction with a component currently r, a in-track component. Again, this is a term from especially satellite terminology. It's a component that's roughly in the track of the orbit, along the roughly the velocity direction. And then a cross-track component. It's sort of perpendicular to the r and x. So just break it up into the radial component, the lambda component, and the h component, the three functions, r, s, and w. So these three are just radial, in-track, and cross-track components. So now what is dh dt? So it's r cross f. Well, r cross the first term is 0 because r and n are descending parallel to each other. So you just get r cross lambda, but r cross lambda is h. Right? R is r times n cross lambda is h. Remember, n, lambda, h. So you get r times s times h. And then you have r cross h, so r cross, I'm left-handed, so I thought I had to do this differently. So r cross h is minus lambda. Okay, so you get minus lambda, and r, and the w component. So again, this makes sense. Angular momentum only changes if you have a component of the force that's either out of the plane or in the direction of velocity, making the velocity get higher and increasing the angular momentum. Radial component doesn't do anything. And similarly, you can do the same thing for dA dt. Again, f cross h, work out all the components, work out that triple product, and you'll get this expression. Notice that all the components, s, r, and w, will affect the runner lens vector. Okay, so let's look at this. What about the magnitude? Rate of change of the magnitude of h. Well, if we just dot h into this, h dh dt, that's 1/2 d by dt of the magnitude of h squared. Dot h into this, we just get h times rs. And if we can divide by h, we just learn that h dot is r times s. Okay? That's just the component in the direction of h. H will only increase in magnitude if there's a component of d by dt in its own direction. So dh dt is r times s. Now let's work out rate of change of h cosine I. But remember, h cosine I, from our definition of these things, is h times the z component of our reference system. So d by dt of this is d by dt of h ez, so it's just h dot ez. So let's just work out all the different sides of this. Time derivative here is h dot cosine I minus h di dt sine I. H dot dotted into ez is minus rw. You have to look up our formulas for lambda and h in that previous slide. So you get the cosine omega plus f for lambda dot ez. And then for h dot ez, you get cosine I, right? H dot ez is just the cosine of the inclination angle, and then rs. So I've just evaluated both sides of this equation. This is just working this out. And this is its definition, but only h changes, so I get that in terms of the disturbed components. The thing is, what is h dot? This is the magnitude of h, is rs. So those two terms cancel each other. And we get a simple formula, the I dt, notice sine I cancels. So the I dt is this divided by h times the cosine of omega plus f. So there's a formula for the rate of change of the inclination of the orbit. Depends only on the out-of-plane component of the disturbing force, which makes sense. The inclination can only change if you have a torque making it change. And so there's our first equations, these are called the Lagrange planetary equations. First equation, the rate of change of an orbit element. And then you can go through each of these in turn. Look at the component of h in the y direction. That's going to be related to omega, the line of nodes. You can plow through using the information we got and get an equation for d capital omega dt. And then you can use the Radial lens vector to get something for d little omega dt, and dE dt, and dA dt, and just plow through step by step and get a set of equations that look like this. So there's our equation for the I dt. Again, I've replaced h with p and I've done other things, but plugged in for r, 1 plus e cosine f, and so on. But there's the equation we saw in the previous view graph. The capital omega dt, using a semilattice rectum here, dp dt, it only depends on s, the component in the lambda direction. Remember, since p is very closely related to angular momentum, it's the magnitude of angular momentum. It's only a force that's in the direction of the velocity that's going to change the total angular momentum. So only s appears in that formula. There's dE dt. It depends on r and s. Some complications there. And there's our formula for the Perry center advance. Involves r, s, and omega together. Okay. Turns out there's also, people often use a composite pericentric angle called, latex is var pi. I'm not sure what it's called. Maybe it's omega, I forget what its real name is, but it's omega plus, it's the variations in omega, this one are variations in this, plus variations in that times cosine I. And so it's just given by the first two terms of this expression. It's kind of a combination of the rate of change of the angle of nodes plus the rate of change of the pericenter direction measured along their two relative directions. Okay? The point is that these 5 first-order differential equations, and there's another analogous equation for that capital T times pericenter passage. Those six first-order differential equations are mathematically equivalent to the 3 second-order differential equations that defined our original problem, our original perturbed capital problem. So it's simply recasting the exact equation, dV dt is equal to the Newtonian bit plus f, into some first-order differential equations for the 6 orbit elements of the oscillating orbit. If f is 0, the orbit elements are constant. S, r, and w will vanish, and so all the orbit elements are constants, as we see in the pure Kepler problem. But if not, then you get perturbations. But generally speaking, these disturbing forces are small compared to the Newtonian acceleration, so you can use perturbation theory. So for example, on the right-hand side, you have these small perturbations. Well, in the right-hand side, you could take all of the places the orbit elements occurred, E, P, omega, and so on, set them equal to constant, and then just integrate with respect to time to get your first-order solution to these equations, just as you do in quantum theory. You put in the unperturbed state on the right-hand side, and take the expectation value using the unperturbed state with the perturbing potential to get the change in the energy levels. You could do the same thing here. It turns out that when you do that, you get both periodic changes in the orbit elements. After all, you have cosines and sines on the right-hand side, so the orbit elements themselves may change in some periodic fashion with many psi bands, depending on what the perturbation is. But you can also get, and these are what often the most important, what are called secular changes. Changes that grow with time. They don't just oscillate back and forth between some fixed 0. They can grow steadily, maybe linearly with time, at least at lowest order. They grow with time and cause a secular change in the orbit that continues to grow as time passes. And the final remark to make is that quite often for various applications, and the ones we'll use will do this, you can convert from d by dt to d by df, work in terms of this true anomaly, which is just an angle between pericenters, just by using the standard thing that d phi dt is h over r squared from Kepler's law, and there are some little extra pieces you have to worry about, only if you're doing higher order perturbation theory. All the applications we're going to work on, we can drop this small effect. So the first order perturbation theory, we can work from the TDF just by using the standard formula that r squared d phi dt, or r squared df dt, is equal to h, the angular momentum. Okay, so any questions about this formal setup before we do some kind of worked examples? Okay, so let's consider some worked examples. So we have a two-body system perturbed by a third body. So you can think of lots of examples. This is Mercury orbiting the Sun, perturbed by Jupiter. This is the pulsar in the white dwarf and the triple pulsar system, or the pulsar in a triple system that was recently in the news. Pulsar in a white dwarf orbited by a third white dwarf, by a third star, which is also a white dwarf. So many applications of this particular problem. Well, let's make some assumptions. So here are the equations of motion, the Newtonian equations of motion. A1 is just a point mass limit of our earlier equation of motion. You get acceleration from each body. A2, you get acceleration from the other two bodies. And what we're interested in is the relative acceleration, right? We're interested in x1 minus x2, a1 minus a2. So if you take the difference between these two accelerations, you get the Newtonian acceleration, right? But then we have the difference between these two things. And let's define everything, let's measure everything from body 2. So let's define the distance r to be r23. So it's this distance from body 3 to body 2. Unit vector is r23. Unit vector is pointing in this direction. M is the total mass of our two-body system. And then we can expand. Notice we have r13, this distance, and that distance. So let's expand this distance about that in powers of r12. Okay, just do a Taylor expansion, and you get this. Okay. In fact, this involves just the STF combination of the unit vector n, the unit vector capital N. Okay, notice that it's still 1 over r squared. This is 1 over r squared. This dimensionally is 1 over r squared, but it grows with separation with distance r. That makes sense because the further apart they are, the bigger the difference in the acceleration from body 3, proportional 1 over r cubed, the distance between the binary system and the third body. And then it has this combination of the unit vector here and the unit vector there, given by that. And then we'll ignore terms of higher order, higher powers of little r over big R. You take them into account if you wish, but we will for this purpose. Okay, so to do our perturbation theory, our Lagrange planetary equations, we have to calculate the radial, the tangential, and out-of-plane components. So you work those out, and you get dot this into n, you get 1 minus 3 n dot n squared, lambda, h, and these coefficients. And now let's just make a simple assumption, just to get a nice simple result. This is what one does in many applications. Let's put our third body on a circular orbit. And so that this n, in terms of our reference system, is just, let's put our body on the xy plane of our reference system. Our third body is on the xy plane, but our binary system will have some arbitrary inclination. And it's just, this unit vector is just ex cosine f plus ey sine f, and f is just related to the orbital period of the third body around the binary system. Okay. And it's just the total mass of the system over r cubed. And we'll assume that this period, this frequency, is small compared to the frequency of the inner binary. So the orbital period of this outer third body is long compared to the orbital period of the inner binary system. Okay, so with this, And with the formulas for n and lambda and h that you saw in the previous diagram in terms of inclination and all those variables, you can work out explicitly what the equations look like. And now we want to convert from d by dt to d by df, because we don't care so much about actual time. Then we want to ask, how do the orbital elements change if you go in true anomaly from 0 to 2 pi? When the inner orbit just goes around one cycle, from one pericenter to the next pericenter, what happens to those orbital elements? Okay, so we take this orbit and just take those equations of motion, those Lagrange planetary equations, and integrate over little f from 0 to 2 pi. But we'll hold big F fixed. That was the thing that determined the unit vector capital N. Let's hold that fixed, because if this body's far enough away, the amount by which it moves in one orbit of our inner binary is going to be small. So we can just let that body sit there for a moment, integrate over one orbit, and then let the thing move, integrate over one orbit, let it move, integrate over one orbit. Basically, we can just average over all the positions of the exterior body. So separate the two, because of the separation of timescales, we can just average over the location of the outer body while integrating over the inner orbit. We want to find out if any orbital elements change secularly with time. Okay, I've said all this in words, integrate over f from over one orbit, holding this fixed, and then average over all positions of the outer body from 0 to 2 pi. And you can make this a little more formal and estimate what errors you're making when you do that, so it can all be done straightforward. Now what you find is the following. The semi-major axis of the inner orbit does not change. There are oscillatory parts of it, but there's no net change over one orbit. So the semi-major axis is constant. And remember, E, for a Keplerian orbit, the energy, is minus 1/2 g. Depends only on A. So this means that the energy of the orbit is constant. The inner orbit does not exchange any energy with the outer orbit. And that's just a result of this approximation where we have these widely separated timescales. So A doesn't change. But the eccentricity changes. It changes in a rather complicated way. It depends on the mass of the third body relative to the mass of the inner system. It depends on A over R cubed. That's no surprise, since we expanded the powers of 1 over R cubed up to 1 over R cubed. Depends on the eccentricity. Depends on the inclination. If the inclination were 0, E would not change. Then it depends on the periastron angle, pericenter angle. So depending on what that angle is, E will change. But the pericenter itself changes. Again, the same overall factor. But it varies in a complicated way. It depends on omega itself, and on the inclination angle, and on the eccentricity. The orbital inclination changes. Similar factor on the front, eccentricity factors looking a bit similar. Notice has the same sine omega, cosine omega, and sine I, cosine I. And finally, the line of nodes also changes. Okay, and then if you want to worry about that combination, this plus this times cosine I, that's how that changes. That will play a role when we talk about Mercury's orbit. Okay, so that's our result for the secular changes. So these things grow orbit by orbit, or change orbit by orbit in that way. Okay, so let's do 2 applications of this and see what happens, see what we find. So the first is to Mercury itself. So Mercury orbits the Sun as a 2-body system, but it's perturbed by all the other planets: Venus, Earth, Mars, Jupiter, and so on. In this case, we have all the orbits are more or less coplanar. So what we have to worry about is this reference angle, because this is the angle of the pericenter relative to the x-axis of our reference direction. The angle of the nodal angle is not so well defined because these inclinations are so small. And furthermore, when you actually measure the orbit of Mercury, you always refer to a fixed reference direction defined by the distant quasar. So this is the relevant angle for describing solar system orbits. this combination of this and this times cosine I, and cosine I is order 1, so that's the variable. When I is 0, this term vanishes, and so all we get is this quantity for the rate of advance of Mercury's perihelion due to the perturbation of the third body. So that's the formula I just showed you. And now we can ask ourselves, how much does Mercury's orbit advance due to other planets? So here's the data for all the other planets. We need to know the radius of the orbit of the other planet in astronomical. This is in astronomical units. Mercury, that's going to be A. Semi-major axis, 0.387 AU. Earth is 1 by definition. Venus, Mars, Jupiter, Saturn. Eccentricity of Venus's orbit, Mercury's orbit is 0.2, so it's a hefty eccentricity. Notice all the inclinations are rather small, so that's why we're choosing them to be 0. If you want to be more fancy, you could worry about those effects. And the mass of each planet is here. It's the inverse mass in units of the solar mass. Okay? So, and here's the orbital period. And so we can work out the effect of each planet on Mercury's orbit. And here's what you get. So for Jupiter, this is the biggest effect. The effect you get is 154 arc seconds per century. So you get a certain number of radians per orbit, but then you take the orbital period of Mercury. That tells you how many radians per orbital period in years. To get a number that's a little easier to deal with, you multiply by 100 to get the rate per century, and you also convert it to arc seconds because that's what astronomers measure. So it turns out to be 154 arc seconds per century. And that's actually quite a good answer. The answer that you get when you really do this carefully, like by just putting everything on a computer and solving by strict numerical integration of the n-body equations of motion, is 153.6. So our crude approximation was actually quite good in this case. For Earth, the effect on Mercury is 62 arc seconds per century, and the more accurately calculated value is 90. So we're quite a ways off. Right? And so why do you think that might be? Sorry?
Earth's closer
Yeah.
Earth's closer to Mercury. Earth is closer to Mercury.
So remember, we expanded in A over R, but R is not so big anymore. So maybe we have to go to higher order in that expansion. So the Earth is a lot closer. The perturbation is bigger. Maybe you have to include higher order terms in that expansion. And there's also another reason that I think plays a bit of a role as well.
General relativistic effects.
Is what?
General relativistic effects.
No, I mean that's a separate thing which we'll get to later on.
Right.
Right. I mean, this is leading up to GR, right? This is the iconic test of GR. But there's another reason why this might not have been such a good approximation.
To mass?
No. Remember, we assumed the orbital period was long compared to the inner period. We had this guy fixed while we integrated over one orbit. Well, for Jupiter, that's not so bad. The period of Jupiter is 5 years. It's 11 years. This is a quarter of a year. That's a factor of 44 or so. So, Jupiter moves like this over one orbit of Mercury. But Earth, this is a factor of 4. So Earth moves by 90 degrees when Mercury goes by one orbit. So this averaging process might not be so accurate. So you might have to do a better job of that when you do the detailed calculation. So this is not such a great result, but we know, at least in principle, how to make it better. Well, this, of course, leads up to general relativity, and I'll talk about general relativity later, tomorrow or probably tomorrow. But let me just say something about this whole story of Mercury, because it really starts with this problem that we discussed just now. And that, of course, is the famous problem of Mercury's orbit. And here's another little history lesson for people who don't follow history. So, when Newton published his Principia in the late 17th century, this is considered a humongous triumph of rational thinking and reason and the Enlightenment over what was considered the fuzzy thinking of the previous eras. But But physically, it was also a great triumph because it explained, for example, the tides of the Earth and the Moon in a very concrete way. You could just simply understand and calculate how the tides worked. It accounted for the advance of the perigee of the node of the Moon due to the perturbation by the Sun. It's again the same calculation we've talked about now. The perigee of the Moon advances because of the perturbing effect of the Sun. It turns out Newton tried to calculate that effect in what are called the Portsmouth papers, and he got it all wrong. In fact, this was considered in those days such an important problem that various societies, like the French Academy of Sciences, offered cash prizes to anyone who could solve the perigee problem for the Moon. And it wasn't solved until the early 1700s by Clairaut, who managed to put together a solution that gave the correct answer, and he won the cash prize. Isn't that great to win cash whenever you solve a physics problem? What a world, right? So these kinds of, but again, when it was done, when Clairaut, the real problem is that, again, it's a problem of a perturbation that you really have to do carefully because the perturbing effect of the Sun on the Earth-Moon system is very strong, relatively speaking. So the lowest order perturbation doesn't give you such a good answer. You really have to be careful. And Newton also made some mathematical errors in his write-up of the solution. So it's a complicated problem that Clairaut finally got. Then came Leverrier, who was an astronomer in France, very ambitious. He pointed out that there were certain anomalies in the orbit of Neptune, in the orbit of Uranus, that couldn't be explained by Newtonian theory. People had been observing Uranus's orbit for many, many years, but it didn't quite fit the Newtonian prediction. And Leverrier was an expert in calculating the perturbations of all the planets, so he worked out all the perturbations, and it still didn't fit. And so he proposed that there must be another planet in the solar system outside Uranus, and he could predict roughly what the orbit was, roughly where it would be, and roughly what its mass would be in order to make the measured orbit of Uranus agree with the theory. And his prediction was so good that within a few months of having it promulgated, German astronomers in Berlin looked in the predicted part of the sky and found a planet, and that's the planet Neptune. Turns out George Couch Adams in England was doing exactly the same calculation and got exactly the same result around the same time, but he failed to publicize the result. And so the credit is generally given to Leverrier. He did the work, but he also published it, essentially, right? So this is a great triumph. And because of Leverrier's triumph with Neptune, he was appointed director of the Paris Observatory. But now that he had a secure position, he had tenure, roughly speaking, he could publish something else that had been bothering him since 1843. Because he was also looking at Mercury and doing exactly the calculations that we did on the previous view graph, working out the perturbations of Mercury's orbit due to all the other planets. And by the middle 1800s, the measured perihelion precession of Mercury was well established. It was about 575 arcseconds per century. And so Leverrier sat down and calculated what each of the planets would contribute to that advance. And there's the 153.6 we got. He obviously did a better job on Earth than we did. He probably went to higher order perturbation theory. Everything, of course, done by hand. He didn't have Maple and Mathematica to help him. Venus produces a hefty amount. Obviously, it's closer. Mars produces almost nothing because it's just far enough away, and Mars is a very light planet. It has very low mass. So it gives nothing. Saturn 7.3. But the trouble is, that does not add up to 575 arcseconds per century. It's 43 arcseconds short of the observed precession. And so what could it possibly be? But Leverrier had the answer. He had just had this huge triumph of predicting another planet because of anomalies in a nearby planet. So why not just do exactly the same thing in the other direction? These anomalies in Mercury's orbit could be explained if you proposed an intra-Mercurial planet inside Mercury's orbit. You could give it the right mass and right orbital elements to give the 43 arcseconds per century. And so he proposed, and various people after him proposed that there must be such a planet. They even had a name for it. They called it Vulcan, after the Roman god of fire, because of course it would have to be a very hot planet being so close to the sun. I believe this is the first time in history of physicists giving a very cool and evocative name to something about which they know absolutely nothing. In modern times, the term dark energy probably plays that same role, right? And for the next 50 years, astronomers searched for Vulcan. Dedicated campaigns, especially during solar eclipses. You can barely see Mercury in front of the sun because it's so close to the sun. It's very hard to see Mercury. So you wait for a solar eclipse and hope that the planet is just outside the moon's blocking the sun, because now there's not so much light, you can actually see stuff. So you hope to see the planet during an eclipse. So during solar eclipses, people wanted to see if they could find Vulcan inside the orbit of Mercury. And indeed, astronomers saw it, they found the planet, but later observations could never confirm these observations. So there were sightings, they were disproved, and for 50 years there was no confirmed evidence of this planet between Mercury and the sun. Adams in England thought he had the answer. If you change the inverse square law, remember if you have a pure inverse square law, you get no perihelion advance. But now if you change the inverse square law from 1 over r squared to 1 over r to the 2.000000157, you can account for that, the missing 43 arcseconds per century. Remember, everything that isn't pure inverse square produces. So just r to the 1 over 2, 1 plus epsilon, you can fit epsilon to get 43 arcseconds per century. So that's what Adams did, and it seemed a perfectly viable solution at the time. The trouble is, it also produces a perigee advance of the moon, and soon thereafter, by the late 1800s, data on the moon got so good that that proposal was ruled out because it violated observations of the moon. So by 1915, when Einstein was working on the general theory of relativity, he was very well aware of this 43 arcsecond problem with Mercury. In fact, many people think that he's kind of discovered this whole thing and proved it in his famous November 1915 paper on general relativity. But it's not exactly true, because he was using the perihelion of Mercury, the known discrepancy, to rule out earlier versions of general relativity that he was working on. In fact, in 1912, he and Marcel Grossmann had what they called the Entwurf theory, a draft theory, a kind of a proposal for a theory. It wasn't pure general relativity in the end, but one of the reasons, he had two reasons for rejecting it. One, it just was really ugly. He didn't like it aesthetically. He was looking for something that satisfied certain principles. But the second reason why he had rejected the Entwurf theory was that it gave the wrong answer for Mercury's perihelion. So already, even before general relativity, he was using this as a filter for possible attempts at a theory of gravity. But then in November 1915, when he was trying desperately to finish his third paper, he promised the Prussian Academy of Sciences that he would give a weekly paper on his new theory in November, yet he wasn't finished. He didn't have the theory yet. He gave 2 talks on the fundamentals of the theory, but he still didn't have it, and he was desperate to get this third talk written. Meanwhile, he knew that David Hilbert was closing in on the theory of gravity, because they had been in communication, and so he was desperate to finish his theory before Hilbert. And so in that weekly period between Lecture 2 and Lecture 3, he figured out the final form of the field equations, calculated the perihelion shift of Mercury, and got 43 arcseconds per century. And then he wrote to a friend, he thought he was having a heart attack when he got this result, because this was like the proof that he was on, this version was the right version. And then he talked about it in the third lecture, and then the fourth lecture he talked about deflection of light, and finished off the series of lectures. But it was like down to the wire with Hilbert. In fact, Hilbert wrote to him later, and some people think that Hilbert deserves credit for the general theory of relativity because he himself was so close, but most historians don't think that's true. But Hilbert wrote to Einstein and said, I can't believe that you could calculate the perihelion advance of Mercury so quickly just after finishing your theory. Einstein didn't tell him that he already had a whole bunch of set formulas for calculating the perihelion advance. He just had to plug in, the numbers from his latest theory, and it would pop the answer. So he had a well-oiled machinery for doing the calculation in advance. He never told Hilbert that. So let Hilbert be impressed. Okay. But that 43 arc seconds per century, and we'll see it later when we get to general relativity, of course resolved the discrepancy and was this great triumph for general relativity. And here are the modern values. So, of course, we now know, in fact, this is even an old chart. I need to update this. So the modern value of the discrepancy is derived from all the 100 years of advances in understanding the solar system that have come along. We know the masses of the planets much better, mainly due to flybys of various spacecraft. We know their orbital parameters much better. We have computer codes that can calculate all these effects much better. In fact, they just simply solve the entire in-body problem for the solar system, including the masses of the asteroids and their orbits. They include basically everything you know about in the solar system. These humongous codes, ephemeris codes that can calculate this stuff. And so the stuff that you need to explain with your favorite theory of gravity is 42.98 arc seconds per century, and this error is now 0.001. It's about 2 parts in 10 to the 5. It's the observational result, and then the accurate prediction of general relativity agrees with the observations precisely. So it continues to be a triumph for general relativity. Okay, any questions about, yeah?
Einstein used some approximations, right? Were they quite accurate?
Einstein?
Did he use some approximations for the precession value to give?
Well, several things. One, the value in those days was not that well known. I mean, it was sort of on the order of 38 arc seconds per century. So it was, I think it was within, maybe 10% or something of the measured, of the known discrepancy. So it took a little bit of time for values to be firmed up in the early 20th and onward. Now, of course, we know it very accurately. But I think he was using what we would today call the Post-Newtonian approximation. I mean, he had everything he needed to this order of accuracy to get the right answer.
And that's probably pretty accurate, right, for Mercury?
Yeah, but I think the point is the values that I showed you for the orbital elements, those are modern values and they weren't known all that well.
Sure.
When it became possible to change to do radar tracking of planets, to bounce radar signals off planets, the value of the semi-major axis changed by about 5%. This was in the 60s, right? So we've learned a lot more about the solar system's size and scale and shape. Half a century after Einstein was doing this. But still, his agreement with the known value then was good enough to claim, victory. Okay. Other questions? Yeah.
Sorry, so did he make this prediction before Schwarzschild came about with his exact experiment?
Right. So yeah, this was before. So this was November 1915. Schwarzschild found the Schwarzschild solution in early 1916. Right, and it was published a little later after Schwarzschild had died. But he didn't use the exact solution. He just used the approximate solution. But again, what today we would call a post-Newtonian solution. He had Newtonian theory plus the suitable correction terms to do the calculation. Okay, let's do another application of this same third body perturbation. So here we want to look at arbitrary inclinations and focus on these three. We won't worry about the line of nodes in this case. So we have a third body orbit and an inner binary that's inclined by an inclination angle I. Here are the secular variations. A doesn't change. But notice, for example, that the inclination, we'll use the convention that I is always between 0 and pi. So between 0 and pi by 2, the orbit is moving in the same direction as the outer orbit. But between pi by 2 and pi, this orbit's flipped, so it's going retrograde relative to the outer orbit. So there's that convention. So notice if I and omega are in a quadrant such that all this is positive, the inclination will increase. I'm sorry, the inclination will decrease as a minus sign. And so if these are all positive, this will decrease, but this is the same quadrant, the eccentricity will increase. So if I have my third bodies on this plane, so I have this inclined orbit like this, the inclination will decrease while the eccentricity increases. Right? So they start to become coplanar, but the orbit gets more elongated. But while this is going on, omega is changing. Right? And in fact, it's advancing as long as this is positive. The sign of this could depend on what omega actually is. So let's suppose omega is increasing. Omega could pass a point where this changes sign, right? If omega crosses pi by 2. So then the thing will reverse. The inclination will start to increase, and the eccentricity will start to decrease and become more circular. So this orbit will go like this, a circular. You should be impressed by the fact that I can actually do this. It's a circular, and then it becomes sort of coplanar, like this. So there's this interchange between eccentricity and inclination, depending on what omega is doing. And if you get the right sign of the inclination, the right relationship between these two things, this could also change sign, and omega could then reverse and change things around. Finally, furthermore, if you notice, if you look at this quantity, take delta E, divide by E squared, 1 minus E squared, multiply by E, and take this guy and multiply by sine I, that guy multiply by cosine I, they cancel each other. So there's a kind of conserved quantity in this equation. And if you think about what that is, that's just 1 minus E squared square root times cosine I. Now if you remember, the angular momentum, h, is equal to the square root, there's a g in here, but mp, which is, forget this g, that's constant, forget the p, that's the square root of a, that's constant, 1 minus e squared, right? So the magnitude of the angular momentum is proportional to the square root of 1 minus e squared. So this, cosine I, is just h cosine I, which is hz. It's the z component of the angular momentum. It's a component of the angular momentum perpendicular to the orbital plane of the third body, and it's constant. Here's my question, and the answer is not 1 or 0. Why? Why do we get this constant of the motion? Remember, you've got a third body orbiting around, perturbing the heck out of things, but you get this Lz that's constant. The reason is that we've taken our third body, the way we did this calculation, and taken its mass and converted it into a wire, a circular wire. Remember, we assumed it was a circular orbit, and we averaged over its position. So that's like taking the mass of that third body and just distributing it in a circular ring around our binary system. That was the approximation we made. Well, a binary system perturbed by a circular ring, what kind of a situation is that? It's axisymmetric. And what is conserved in an axisymmetric system? Lz. Okay. So it's really, of course, it's a result of the approximations that we made, but it's very cute to have this. It's an approximate conservation, right? Because you have made an approximation in converting this third body into a wire, but it's conserved. So as again, you see as E increases, I decreases. So you get this effect just from the conservation of this Lz. Note, another thing you see from this equation, this set of equations, is that there's a stationary point. There's a critical value of the pericenter, either pi by 2 or 3 pi by 2, where if it's pi by 2, then cosine omega is 0, cosine omega is 0, so these two are constant. If these two are constant, then everything here is constant, and then this will be constant as long as this thing satisfies a constraint, and you can work out that constraint as given by that. So with a certain eccentricity and a certain inclination, then and a certain orientation of the orbit, there's a fixed point in these equations. So that's an orbit that is inclined relative to the third body's orbit, which is, remember, we approximate as a wire, but in which the pericenter is pointing, perpendicular to the line of nodes, right? It's pi by 2. If omega were 0, the pericenter would lie along the line of nodes. So in fact, it's pointing perpendicular to the line of nodes. The ellipse is perfectly symmetric relative to the orbital plane. And 3 pi by 2 is just the other way around. It's the trivial inversion. It turns out that's a critical point, and when you put in other perturbations, it's a point where you then get a stationary solution, and orbits will tend to converge or collect at that point. And it turns out that there are asteroids in the solar system whose orbits have these orbital characteristics. They're highly inclined, but their pericenters are always either pi by 2 or 3 pi by 2, relative to, in this case, Jupiter, because that's the biggest third body in the solar system to perturb them. So if you compare with Jupiter's orbit, then so there's a collection. There are asteroids whose orbits collect around this particular stationary point. And then, of course, they don't stay there exactly. There are perturbations, but they tend to oscillate around this stationary point with particular frequencies called Cosy Resonances. And this phenomenon was discovered independently by Cosy in Japan and Lidov in the USSR, who were studying. Cosy was studying asteroids, and Lidov was studying artificial satellite orbits around the Earth. They both discovered this phenomenon of both this interchange between E and I and these stationary points and the resonant phenomena that you can get. And in Cosy's case, of course, they explain long-standing observations of asteroid behavior in the solar system. And just to give you a quick example of what this might look like, here's just a simple plot. I don't even remember what the parameters were showing. Here's the eccentricity starting from a very, very small value, going up to 0.97, and then just oscillating back and forth. This is on a long time scale. It's a time scale determined by the mass of the third body, the separation of the third body, and so on. So it's a long compared to the orbital period. So the eccentricity oscillates, while the inclination goes from whatever its initial value was to a new value. So it oscillates. And the pericenter advances and then it tails off. It actually, I think, reverses a little bit during these peak oscillations. So it kind of wobbles a bit as it evolves. So you get all kinds of weird behavior when you include this Cosy-Lidov mechanism. And here's an application of this mechanism in a context that we might be interested in for gravitational waves. So you could imagine a supermassive black hole in the center of a galaxy with a cloud of stars or other black holes surrounding it. These objects are predominantly are dominated by the gravitational field of the black hole, so they're on Keplerian orbits in first order, but they do perturb each other. And you can ask yourself, what do those perturbations produce? What's the result of those perturbations? And people have been considering these problems for a long time, and using n-body codes developed by David Marital, Alexander, and Seppo McCullough, with me as a theoretical groupie just saying, good work, boys. These people are the real experts. I mean, they have these fabulous n-body codes that can do all close encounters of stars with each other. It's amazing the kinds of simulations they can do. But the question was, how does such a cluster evolve with time? And what's plotted here is the semi-major axis of a star, and this is the eccentricity, or 1 minus the eccentricity. So this is 1 minus 10 to the minus 4, and this is 0, so this is circular, and this is extremely eccentric. And you see the orbits evolve. They're all perturbing each other, but they evolve with A not changing much at all. Again, that conservation of energy, A doesn't change because they don't interchange much energy with each other. But their eccentricities change, and if the eccentricity gets so high that the pericenter of the orbit gets close enough to the black hole that the star will be captured by the black hole and not come back up. It will disappear from the cluster. And so you see stars getting so close that they get captured, and that will change. But on the way to being captured, they'll orbit the black hole very closely and emit a burst of gravitational waves, and that is something that can be detected by the LISA space-based detector. And so simulations like this can be used, for example, to estimate, given some cluster characteristics, what is the rate of production of EMRIs, extreme mass ratio inspirals, very eccentric orbits of small bodies around supermassive black holes that would emit gravitational waves from LISA. And so you can make this simulation, and this is really the Kodai Litoff effect in action, but in a collective situation where there are many combinations of resonant behavior that kind of enhance the effect in certain ways. It turns out, however, that if you include general relativity, if you include the perihelion advance induced by general relativity, it actually suppresses this effect. There's a kind of barrier here that reduces the ability of stars to get such high eccentricities that they get immediately captured by the black hole. And in this work, we estimated how that affected the rate of growth of EMRIs. Generally speaking, general relativity has the effect of suppressing the Cosy Resonances phenomenon, mainly because it makes omega advance no matter what you do. Right? The Cosy resonances occur because omega can increase, but then it can decrease. And while it's doing this, increasing and decreasing, you get these huge eccentricity growths. But general relativity, even though while your Cosy is trying to make the omega go backwards, GR is pushing that guy to go forward all the time. It's relentless. Right? You cannot get away from general relativity, pushing it forward, and that kills this kind of resonant behavior. So it turns out to suppress this growth of eccentricity in a fairly dramatic way. So anyway, that's just another example of this Cosy mechanism in action. Okay, let's do another worked example. Ooh. Or maybe let's not. It's 5 o'clock already. Fine, so what I'm going to do is say, let's do this other example tomorrow. Associated body with a quadrupole moment, which has applications both for Mercury and the Earth and many other things. And then I think after that, we will be very close to starting to talk about general relativity. Any questions before everyone rushes off? Yeah.
So how does the Cosy mechanism change if you don't orbit average? Does it vanish if the third body is moving really fast?
Well, it gets more. I mean, obviously, when these kinds of approximations, right, large separation of distances, large separations of scales, when they are no longer valid, then you have a standard three-body problem, for which there's no analytic solution. In fact, many mathematical physicists have spent careers trying to solve the unrestricted three-body problem. This problem here is a particular case of problems called the hierarchical three-body problem. So there's a hierarchy of scales. In that case, you can use these approximations, and of course, you can do a better job of these approximations. They're not done. This is just the crudest version. In the hierarchical problem, then, there are techniques that you can use to do these averages and get some analytic results that you can then compare with observations. But when any of those approximations break down, then you just have the full three-body problem, and the best you can do is slap it on a computer. And we know the three-body problem is in any case chaotic. So you have the whole issues of how long you can integrate these things. So that's why people stay with the hierarchical. Yeah.
I think this might be a somewhat related question. Back on the first slide where you drew the diagram for the three-body system, you define capital R between the third body and the second body. I guess you're anticipating there that the second body is the heavy one. But if you had a comparable mass binary, wouldn't you do it relative to the center mass?
Yeah, so I mean, that was kind of just a very simplified thing. In real practice, you always define the center mass of the inner binary, and then find the third body relative to that center mass. And it turns out that if you have comparable masses in the inner binary, the approximation of a circular outer binary is no longer good, because the quadrupole moment of the inner binary perturbs the outer binary and makes it non-circular. So to do a better job than this, especially for comparable masses, you really have to include the perturbations of the third body as well and do it as a whole. Right? And this is what people in hierarchical three-body problems, that's their day jobs. That's what they do. You know, do this, but way much better than we've done. And there are people working on hierarchical four-body problems, two binaries interacting with each other, especially for binary black holes in the field of a binary supermassive black hole system in the center of a merged galaxy, blah, blah, blah. So you can really go crazy with it. Other questions? Okay, so tomorrow I'm on at 9 o'clock, right? 9:30? Okay. Sleep in.